today's keynote. Today's keynote is different than usual. Usually we have one keynoter. Today we have a trio keynoter. It's a new initiative, a new idea that Jeff came up with, Jeff Rarick, who is our vice program chair. So I'll ask Jeff to come and introduce the concept as well as invite the speakers. Jeff.
Thank you, Yaron. And if we could get the title slide put up, Luca, I will introduce today's keynote. It's going to be a little non-conventional. So let's start at the beginning, not the end. But anyway, thank you. And yeah, here's to the next 40 years of ITCs. All right, so today's keynote is going to be a little different. We're not going to have a typical keynote from just one industry leader. We're actually going to have three. But to get you guys motivated, a little audience participation at the beginning. How many of you have worked in this field for more than 10 years? I'm guessing a lot of hands are going to go up. All right, how about more than 20 years? Okay, keep your hands up. More than 30 years? All right, oh good, we still have a few. More than 40 years? All right, just a couple left. How many of you that have been here for 40 years have done it all for the same company? Anybody? Oh, we do have another one. A couple over. All right, great. All right, so one of our speakers today is in that category. All right, how many of you people, different question, how many of you people have written an ITC paper? Okay. How many of you have received a best paper award for one of these? Oh, we do have a few, that's good. How many of you received 2 best paper awards? Not too many left. All right, another one of our speakers has that designation. All right, last question. So how many of you have been a VP of manufacturing for a startup company? How many of you have been a creator of one of the world's leading ATE equipment manufacturers? All right, I have another one. How many of you have written a state-of-the-art path delay ATPG program? Not too many. How many of you have done all 3 of those? All right, our third speaker has that designation. All right, so with that in mind, I'm going to bring up our 3 speakers. So I'll have Mike, Tim, and Grady come up to the stage. So let's give them a warm welcome. And what I should say, how did we pick these 3 guys? It's actually been a complete honor for me to have worked with these gentlemen for the last 16 years while I've been at AMD. And I thought I would offer to the steering committee to say, hey, how would you like to share some of this incredible experience, with these guys? And they said, yeah, let's do that. So we're going to have a conversation. And just in case you guys are mathematicians in the audience, the title is a little bit wrong. It's actually 128 years of test experience. Okay, so let's go ahead and first I'll introduce Grady Giles. Grady has a BS in physics from Texas A&M University. He started at TI in 1978, moved to Motorola, spent some time there, came to AMD, and recently retired after 22 years. Grady may or may not tell the anecdote today about he was honored at a bar at the St. Louis airport for some of his technical contributions. We'll see if he tells that story. Tim has a BSEE from the Rensselaer Polytechnic Institute. He started at AMD in 1982, and he stayed at AMD, so 40 years. Just celebrated that a couple of months ago. And anecdotally, Tim is an Ironman triathlete and is in training. If he looks particularly shapely now, it's because he's in training for the Chicago Marathon in about 10 days. And Mike Bienek, also Texas A&M. Started at Motorola in 78, did several startups and covered quite a bit of ground, a lot of time at Convex, and then a bunch of time at AMD, 18 years. And if you can get Mike drunk enough, he'll tell you the story about why he is technically, should be called Sir Mike Bienek. All right, so those are our 3 things. The way we're going to do this is we're going to just have a conversation. We've got a rough outline that we'll follow. We'll talk about some industry trends. We'll talk about ITC. We'll talk about the lessons we learned to get to the title of this keynote. And we'll talk about the future. So let's just jump right in. I'll kick this off. Tim, you've been doing this for a long time in the industry with one company. Let's talk about the drivers that you've seen with the industry.
Okay, not as long as these 2, but kind of, I'm the young guy in the middle of the old guys here.
Tim's a relatively inexperienced one.
Yeah, so when I started 4 decades ago, I was working in a microprocessor peripheral group. And this is back when PC boards actually had a number of discrete components on them. And I started as a test engineer in that group, and my first product was a 16-bit DMA controller. And it was fabbed in an NMOS process, and it would be a couple more years before we actually moved over to CMOS. And I remember seeing people taking Rubylith over to light tables and manually doing DRC checks by looking at that Rubylith on a light table. So we've certainly come a long ways from in those 4 decades, and that's been driven by Moore's Law, where we've had a doubling of speed and capacity every couple of years. And the number of test pins has remained relatively constant over those years, but the amount of transistors that we've had to test within the die has grown exponentially. And the amazing thing is the DFT community has done a pretty good job of keeping test time and test cost relatively constant in that time. And the stuck-up fault model, I think, has served the community well for a lot of that 4 decades. But obviously, in the 90s, we started to see additional fault models get introduced: IDDQ, path delay, transition, and more recently, more advanced fault models, user-defined fault models, cell-aware opens, bridges, things of that nature, as devices have gotten more complex and the geometries go down. And I guess maybe the final note there is, if you have a mature process, maybe you're a generation or 2 behind, and defectivity levels are pretty low in that process, and your yields are pretty high. Well, you don't need to be as vigilant as going after test coverage on that sort of process as you would if you are on the bleeding edge in a process that may not quite be as mature. Defectivity levels are a little bit higher. You need to be extra vigilant about the kind of fault models that you're applying and the test patterns that you're applying for your devices to hit DPPM levels.
Great, thanks, Tim. That's a good set of drivers. Mike, you've been kind of associated with the tester, the ATE community for a lot of your time. Why don't you give us a background on that?
Yeah, so the first 10 years of my career, I worked at Megatest. They made desktop testers for EEPROMs and for RAMs and for logic, and eventually went on to do Big Iron, doing the world's first per pin architecture. And that worked really well back in the day because we did all functional testing. And of course, the pin to gate ratio made that possible. But one of the interesting stories, I had a guy one time come up and say, "I've just developed the world's fastest part. Can your tester test it?" The answer was yes, because you can always do architectural things to improve the speed over a single component. But it was an interesting question. It was not too long after that, I saw a paper on silicon on sapphire, and it was 40x the speed of the testers. And it's like, well, how did they measure those gates if it's 40x the speed of the testers? Simple answer: ring oscillators. And I thought, well, that's a one-off type thing application. Later, I discovered Cray was able to test their really fast devices, and they were essentially putting a LSFR on the inputs, Miser on the outputs, and LBIST, but functionally testing their parts and able to get the yields where they needed them to build their supercomputers. And it started to dawn on me that if you build your tester on chip, then the tester speed always tracks the technology. And of course, after that, we had JTAG come along, and that gave us an interface in and an explosion of built-in self-test. And people began to predict the demise of Big Iron. Now, that didn't happen, and I think there's couple of reasons for it. One is companies are resistant to change. If they have infrastructure they paid for, they're going to keep using it. A second thing is Big Iron is very precise, gives you a lot of characterization capability. But the third thing that's really preserved them is you started using that static memory for structural testing, broadside testing of ATPG. And over the years, that's continued to advance. You have techniques like test compress that let you put even more test content into vector memory and keep running. We always talk about Big Iron, but the other ATE that's out there is SLT, and it's kind of interesting that where the large testers were eventually structural or functional and moved to structural. We're now adding another tester to put that functional back in and continue to get the coverage we need, especially in the microprocessor market.
Yeah.
And we didn't talk about that, Jeff, but all of us are coming from a microprocessor background. If you're into analog or other disciplines, you might find some of what we're saying a little specific to our industry.
That is true. So Mike, you kind of presaged, DFT being a threat to the big iron testers and all that. Grady was one of the people that kind of kicked a lot of that off. So Grady, tell us about, some DFT history here.
Well, let's see. I started at TI, and I went, and about 3 years I went to Motorola. Anyway, both of those, like TI had a 9900 microprocessor. I was a product engineer on, and then got that Motorola. They had the 68,000, and both of those had one test mode, and it was the same test mode. And it was they each had a single test mode, and they're separated by about 3 or 4 years. And the single test mode was dump the control ROM data. Anyway, so at time zero, DFT was a memory test. So in our industry, and especially microprocessors, it's been dominated by state-of-the-art microprocessors and memories, and microprocessors have embedded within them lots and lots of memories. Early on, doing DFT, it was what we called novel extensions to existing architecture, or ad hoc addition of test hooks. And it started out with little islands of things that we would do these little tricks with, gain access to some PLAs, or like the direct access to some embedded memories, things like that. And then that over time that morphed into maybe a few scan chains here and there, and that just at some point it flipped. And really the flip in my experience came with when about the time JTAG hit the fan. About that time, DFT as a profession, it took off. At that time, there were all these 4-letter acronyms, IDDQ, JTAG, LSSD, BIST. Anyway, that was all going on about that same time, and that created, it seems like it created a space for the profession of DFT to take hold, and it had more currency, and if you had a big design project, you pretty much had to have a rec for a DFT guy. And I think that happened about roughly very late 80s or early 90s. During that time, there was a lot of controversy, or a lot of politics about DFT overhead. And like one time, there was a industry executive that came here and said, "We don't need no stinking DFT." but another time, Ben Bennett's, he said a more inspirational note. Don't think of the DFT overhead as overhead. It's an investment, and it's necessary. You can't sell them without testing them, and you have to do a good job of testing them. And the scale, it was just impossible to keep up with the functional pattern. So we had an inflection point of going from primarily functional, then this ad hoc thing, and then at some point, the bigger serious designs just had to flip to structure design. And I'm a scan guy.
Right, and I think Grady, that change to more structural methods enabled a lot more automation as well. And Tim, you've kind of been the beneficiary of a lot of that, as you've seen. So tell us about automation and how that flowed in.
Yeah, I guess before I get to that, I mean, my story is somewhat similar to Grady's. I started out as a test engineer, which was really kind of a DFT engineer in disguise at that point, because you were responsible for getting patterns over to the tester, and you had to work with the design folks to go through the schematics, see where there were potentially difficult areas to test. One example of that might be counters that were long, so you put in ad hoc DFT solutions to maybe break that up, make things go a little bit faster. But the focus was really still on functional patterns, writing those to get them to the tester, and they had to be synchronous with the tester, and depending on when you applied the output or inputs, the outputs had to be deterministic with the tester. So that was kind of the path we proceeded down for a long time, and that got more and more challenging as the speed of the devices went up and more clock sources were added to devices. And eventually I started doing DFT a little more full-time out of test engineering and more into DFT as a career, and I was in the microprocessor arena. We were still doing a lot of functional patterns and fault simulating those, and writing a lot of assembly code, fault simulating it, learning how bad you are at actually covering stuck at fault models and having to iterate on that. And it was very labor intensive and time consuming. There we go. Yes, my mic's still on.
It's on.
Okay. The volume went down all of a sudden. So it was very labor intensive and time consuming process. And there was a lot of concern, like Grady had mentioned, about DFT overhead in the early days. So it was that structural DFT was more limited to difficult to test control logic and perhaps memories where it was easier to implement some sort of self-test solution with a lot of area overhead. But the big switch happened at AMD when we acquired a company called NextGen that was building an x86 processor, and it was being fabbed by IBM. And one of IBM's rules for fabbing devices was it needed to be full scan. So that really started to change the mindset at AMD. It kind of showed it was possible to put in full structural DFT solutions. And thank you to IBM for insisting on that, because that made my life a lot easier from there forward. So we began to see complaints about DFT overhead diminishing, and you could also leverage that DFT that you had to provide additional benefits. One example of that is using scan for debug to help get parts into the field faster once you fabricated it. And really that emergence of EDA and CAD in the 90s, I think really was a big driver for getting structural DFT into the mainstream from being more point solution pioneered by individual companies.
Great. All right. And I think what we've all seen along the way here is that that trajectory that we just talked about and how the industry evolved was facilitated a lot by standards. Grady, you were instrumental in probably the first and most important standard here about JTAG. Why don't you go ahead and get that part started?
Well, yeah, JTAG, it was a weird trip for me because I was the only IC test guy there. I mean, there were some people that had involvement in IC tests, but I mean, all the other players were all board test people. And anyway, I felt a little bit put upon by some of that, but in the end, they were right, and they were also wrong both. I mean, the standard became necessary for I mean, it was board tests. They needed it badly because a bed of nails was just not scalable, and all the multi-level boards and multi-level interconnect on the boards and everything was just making it untenable for them. And I just didn't see how it was useful for testing chips. But okay, I went along with it. Well, in the end, they use it for board tests, but not really nearly as much as we use it for chip tests. That's how they were wrong, and I was right. and today, like some of the AMD microprocessors, we have literally millions of JTAG bits, not even regular scan bits, millions of JTAG bits, TDR bits. And it's used for primarily test mode enablement or device configuration of different kinds of stuff. It's some test data collection, but mostly test mode enablement features. The little anecdote was, I mean, a few years after JTAG came out, I really had my only interaction with some board test people that are actually using it. I was at an airport, Seattle airport, and a layover, and I was one of the only people in the bar, and there's the other two people in the bar, and so I couldn't help but overhear what they were talking about. And they were talking, I heard Shift DR, and I was coming back from the ITC, and I thought, well, these guys must be these guys must be fellow wayfarers coming back from the ITC, and I'll make a conversation with, oh yeah, you coming? No, they didn't even know about the ITC. And they were talking JTAG, and I go, really? Yeah, well, I've got my name all over that. And they pulled out the standards, a leaf-eared thing, and right there on the front page there. I was on the working group and the balloting group, and they got down and they praised me like. Well, anyway, so that was my interaction with board test people.
Thanks, Grady. And I guess the moral of the story is participate on standards, and you too could be worshipped in the airport bar. So Tim, at AMD, then after JTAG kind of gained some ground, did that help you in your mission as a DFT pioneer?
Yeah, it definitely did. I never had any interaction with board test people, but I certainly leveraged the fact that we had 5 dedicated test pins that I could sell to my management that we needed to support board test people, though in reality, I'm not sure how many of AMD's customers were using it at that point in time, but that didn't stop me from pushing it and selling it. So it was a real game changer for me, right? Because it added the ability to add a number of additional test modes and features through those dedicated pins that I didn't have to fight for on every product again. It was just going to be there, and it just changed things in a dramatic way for me. Yeah.
That's great. And Mike, you've been the beneficiary of extending some JTAG stuff into, other realms and all that. And there's a bit of a legacy now built on .1. So tell us about the other places you've seen it show up.
Well, I started using JTAG even before the standard was official because we had people participating in that. And I was also working for convex supercomputers at the time. And because of the reliability that you need in military and avionics and other supercomputer things, they were willing to invest in the test and the DFT overhead. And I think you have to really admire JTAG. It's over 30 years now, and that standard and that interface is still being used. And that speaks a lot to that, as well as we're continuing to enhance it with the, even lately with 1500, 1687 analog. And the only thing that it's falling short on now and is being addressed by standards is the bandwidth that those pins give you. So I think if we get the bandwidth up to handle the new test content, then JTAG's still going to be prevalent in our industry.
Great. All right, so that's a good kind of a running start into the evolution of the industry and stuff. Before we get into the lessons learned, I wanted to spend a little time, since we're at ITC, let's talk about ITC a little bit. So, Grady, this is what, your 39th ITC, I think?
My 39th ITC.
39th. So give us some reflections on ITC.
Yeah, I've been coming here every year since 1983, except for 2018 by court order. I had a jury duty. But so ITC, I mean, I just eat this stuff up here. When I came, I was the first time, several times I come, I was a real greenhorn, and I was just learning how to be an engineer. I wasn't even trained as an engineer. I was a physics guy from college. And I just ate up all the stuff. There are all these Mount Rushmore types that I really looked up to, especially Tom Williams, Ray Mercer. I mean, there's so many more. Ed McCluskey, Janek Patel, Sudhakar Reddy, Paul Bardell, lots of people, lots and lots of people. I just owe so much to, just voraciously consuming their content they presented here. And they were all very generous. And I mean, over time, I mean, I learned kind of the academic approach to all that. I'm not trying to toot my horn too much, but my level of contribution has been competitive with all these PhDs that I've looked up to. ITC had lots of politics and controversy. I mean, I was talking about we don't need no stinking DFT, but like Tom Williams would come and he was always plugging LSSD versus MUXD. There was some tension between like Motorola presented a bunch of structured design stuff. Intel didn't. I mean, they presented more ad hoc stuff or lots of fault simulation. I mean, in those days. But it was a platform for lots of, cross-fertilization, I mean, between industry and academia. And I mean, that's how I got to be who I am.
And, Mike, you attended a few ITCs, but might have a more contrarian perspective on the conference. So what do you think about it?
Oh, I don't know that it's contrary or not, but when I was at Convex, I moved from testers and into BIST on the chip, as well as writing a lot of software. Jeff mentioned the ATPG program. I'll talk more on that later. But I would come to ITC just to benchmark what I was doing against, what is state of the art. And it was really interesting to watch that there's a lot of feedback between the people developing circuits and EDA and how that continued to evolve. And here we are 40 years later. I'm sitting in meetings yesterday and we're seeing there's still evolution and improvement to be had. We keep learning and doing things. So that pace has continued. However, the contrary part is I always pointed out that state of the art lags the need by quite a bit. And what I mean by that is if I see some sort of problem coming up and I want to address it with a new technique, by the time I define it, get a product intercept point to try it out, we go through design, we go through fab, we go through getting the parts, debugging, and get enough data on it, it can easily be a half dozen years. And the same applies to the standards. If we look at especially like 1687, it can be well over a half dozen years on that from the time you have a need till you finish it. That doesn't detract from ITC though, and that's why I say not contrary, because the people that are 2 or 3 nodes back are getting very stable EDA tools and know what to expect as they move forward toward the bleeding edge. And even the bleeding edge people benefit a lot because we are influencing EDA to address the needs, as well as standards have allowed us to interchange IP and now the test content with 1687. So I think even the bleeding edge companies get a lot out of this conference. So that's why I say I'm not contrary.
Yeah, good point. All right, and Tim, what are your experiences with ITC?
Well, I haven't attended nearly as often as Grady, not even close, I think. But I was also a consumer of ITC proceedings when I wasn't able to attend in person. As I mentioned earlier, I started out as a test engineer, and my boss at the time had a number of ITC conference proceedings on her bookshelf, and I found myself drawn to that, going through and reading those things and trying to apply it to what I was doing as a test engineer. And I was fortunate earlier in my career as a test guy to be able to attend ITC. And I was always drawn to the paper sessions more than the floor show, even though I probably should have been more focused on that being a test engineer. But in those days, the floor was dominated by the big iron AT companies, and they had some pretty outrageous parties in some of those shares. So they're obviously making a lot of money. And in the 90s, I think you started to see that switch where the floor was, and the booths were now dominated more by EDA and CAD companies. And kind of late 80s, early 90s, I started moving more full-time into DFT, particularly in the microprocessor space. And one particular session at ITC that was very important to me was the microprocessor test session, which I think Grady chaired for a number of years. And I learned a lot from the people that preceded me and what they were doing with their designs, and I was able to reciprocate on that a couple of times following that. So I've certainly learned a lot from those that presented in those sessions, and helped to try to do the same myself. And I think when I started doing those presentations, the process, at least at A&D, was a little bit less formal for getting things approved, and not as difficult, but certainly I think more lately you can still do paper presentations, but the number of hurdles and approvals that you have to go through is a lot more formal and rigorous. So it's not as easy as, in my view, as what it used to be. And I think you also see that there have been some major players in the industry that have never presented at this conference. And I don't think that's due to a lack of desire on the engineers there to want to present. It's simply a matter of company policy that they're not allowed to, which is a little bit unfortunate given the sharing that goes on here. But one thing that Phil and I started doing a few years back was this industry test challenges session, and that's kind of an informal way. It's not recorded.
I like to call it ITC at ITC.
Yeah, it's kind of an informal way to share data and controversies that allows people to dive a little deeper than maybe the more formal portion of that. So, you know, ITC and conference proceedings, they've been a big factor in my career development.
Thanks, Tim. And I'll take that opportunity to make a shameless plug as next year's program chair. I would love for you guys to submit lots of papers. So put pressure on your managers to let you publish and share. This is a really important thing for the community. So ITC has been really great for that. All right, let's take this now into the lessons learned. This is why we're here. This is what we wanted to talk about. You know, and you know, draw on the extensive experience of these guys to say, you know, what really mattered to you and what lessons did you take away? So Mike, why don't you kick us off with that?
All right, so the first of 3 lessons is don't believe what you think. I saw that on a bumper sticker one time, and like most Dilbert cartoons, it was relevant to what I was dealing with management at the time. In the old days, we had a small die. If you put a thermal head on it, you believed that you had that temperature across the whole die. And on that small die, if you program the ATE to a voltage, you assume the whole voltage plane across that die was 1 voltage, even though I've got anecdotes about setting up voltage planes to oscillate and cause problems, even in the early days. And so as we got to SoC and larger components, one of the things you'd find is you'd have a section of memory that's running very cool, and then you'd have a GPU or a FPU off to the side that's cranking away. And I know we've presented here before that on these larger die, you can have a 35-degree thermal gradient across the part, even with a heat slug and a heat sink on it, or a thermal solution on top of it. So since our transistor performance is a function of temperature and voltage, not having a consistent set of values on the die is problematic to testing. And it's not that the laws of physics have changed, it's just that second and third order effects become more important as you do go to the different nodes. Let me give you a good way to explain heat density to your managers or people that don't understand it. If I take a magnifying glass, 6 inches, hold it out in the Texas sun in the summer, it gathers about 10 watts of energy. If you put your hand right under that glass, the temperature on your hand is air temperature. As you move down that cold cone of light, eventually you're going to jerk your hand away because you don't want to brand yourself. That's the same thing that happens in node shrinks. The nodes are set to be half the area with each shrink, right? Since most of you guys can do binary math, you know that 10 divisions like that gives you 1,000 times the heat density. And it's just impossible to move those kind of temperatures right away. A second example of how scaling changes. Way back in the day, if you wrote a timing analysis package, you only added up gates. Later, we had to look at the loads on those gates, not for the absolute current, but for how it affected transition speeds. And as the timing kept going up, we had to take care of the time of flight on wires. And then you started looking at the edge rates that were generated as it flowed down the wire, and eventually how adjacent wires interfered and could accelerate or decelerate signals that are on there. And I'll give you a third example here of smaller geometries or DIDTs. When I was working at Megatest, we were doing a tester shootout at Texas Instruments. And you had to prove your own testers' reliability and that you met your own specs. The way they did it was take some NIST certified cables that were a certain length, and they would come in and plug them from any input to any output, and could you repeatedly make the same measurements and get the correct results on the wires. So to test out our program, we made our own cables, put it on there, and we would sit there running to see if we were good, and we would notice now and then the timing generator would glitch. In a way, it was our own version of SDC, some data corruption, right? It's like, what was happening to make the tester glitch? And we eventually traced it down. It was when the air conditioning system came on and off. That DIDT event would go through their power conditioner, through the testers, power supplies in the bays, make it all the way to the timing card, and would move that edge. And you have to realize any event, we all talk about, we have decoupling capacitors. Well, they have a response time. And any event, you're responding to it after the fact. Capacitors, do you know what the ESR is on a capacitor? When I was doing really high-speed stuff, it's like, how long does it take that capacitor? And we're getting into the time frames where that capacitor becomes an effect you need to be aware of. So being aware of all these facts and having that presented, that's part of the reason why you're at ITC, to learn about problems other people have experienced. Lesson number 2, don't believe everything you learn at ITC. And the reason I say that, it's tongue in cheek, is because the first person to encounter a problem and write the paper may not have found the optimal solution, or may be optimizing for something different than what you want to address. A couple of examples on that. About a dozen years ago, I built a PLL tester to get the full transfer function of a PLL, jitter and spectrum of everything. And the noise floor on that tester was about 100 femtoseconds. And best of all, the DFT you had to put on the part to support that was 1 extra pin, reusing 1 extra pin, 2 registers, and a handful of combinatorial gates. And you've never seen that published at ITC. You have seen things published on PLL testing in ITC, and there's some excellent papers here, but they were optimized for putting PLL BIST. And so the techniques that you can use on die and what you can do off die and the accuracy you can get with those things changes. So there was room to develop over what had been published here. Jeff also talked about, I did a ATPG. Well, it was AC, path delay, robust level 4, and I used some algorithms that still aren't used in the industry today. This was when I was at Convex. We got 66% coverage of all gates in the design for speed. Like I said, they were willing to devote. We had a CTO who said we have to have quality because we're going into mission critical markets. We topped off with 33% of DC stuck at test. Again, something that's not published. That's a software example instead of hardware. Third, algorithms. I had built a board and it had all JTAG parts. I thought I will see what would it take to verify all wires are not open, they're not shorted to power or ground, they're not shorted to any other wire in the design. And so I worked on it for a while. And then I asked Jeff, it's like, Jeff, how many patterns does it take to verify that for a board with 4096 wires? And Jeff knew the answers. Kind of surprised me. He keeps up with all these papers and has an excellent memory for it. And he said, well, the answer was published a few years back. It is 2 times log 2 of the number of wires.
Ken Wagner, right?
Yep. So he said 24. I said, all right, the algorithm I just developed does it in log 2 of the wires plus 1, or 13. You remember this discussion, and was the number correct?
Yeah, I tried to tell Mike, oh, you can't be right. There's an expert that says this is the right answer. Until Mike actually wrote out the patterns, I'm like, oh, wow, you ought to publish that.
And I never did. So the thing is, you can always learn and improve and do more than what we've done here today. Like we talked about, ITC has continued to have a pretty good pace. And I will give you the final part of lesson 1 about things changing. I inherited a book. It's an encyclopedia. It's called the Lincoln Library of Essential Information. It's this huge, thick book. It was published in 1924, and it debunks science fiction saying it's impossible for man to ever travel to the moon. Times change, and what we can do changes. So lesson 3, don't get behind the curve. And what I mean by this is there is a lot of good information published here. The problem is you don't always get to implement it in your parts because you're going to fight your manager about whether doing the extra time and silicon and putting it all on there. However, that same manager is going to walk into your office one day and say, we've decided to do this big SOC. Are you ready to test the memories, the logic, the high-speed interfaces? We're putting wireless on there, and we're going to do an optical interconnect. Well, it's going to take you a generation or 2 of using techniques and proving out your production flow with them. And so if you're not preparing for that coming down the road, you're getting behind the curve. When I was at Convex, I had my own supercomputer and did that ATPG. And it took that supercomputer and every bit on it and every cycle to be able to take all of our devices and generate patterns, and then those linked into a board, and then those linked into a system so we could do the full system test. With the size of today's components, you need to be doing that at the IP level so that you can divide, conquer, save, link things together, or as it's called, retarget. And so I would, as my final piece of advice, would say if you're not on board with 1687, you should be.
All right, good advice. Grady, you've learned a few things in your years. What are your lessons?
Where's my clicker there? Okay. Yeah. My first thing, it's not the first one on the list, but it really starts with understand the gaps of whatever project you're undertaking. And you start with looking at the last time you had to do this problem or the new problem, but you're looking at the beginning of the project. You're looking at what don't I have that I really need or I could use or I could leverage that would advance the state of the art, that this is a new project and it's bleeding edge. I'm always looking, you got to do that early and identify new inventions or new CAD algorithms or something like that. And so that goes with get your hands dirty, dig in, and innovate. I mean, over the years, I've presented, several times here, but almost everything I've ever done here, shown here, started out like that. I mean, I had one of my first big paper was testing content addressable memories. We had at Motorola, we had a memory management unit, had a translation lookup table. It was a CAM, and I looked around. There was no papers on testing CAMs, and I was able to come up with a CAM test algorithm, which was the first paper on testing CAMs, and JTAG and implementations, and we had something called we call it MICTAM, but the paper was test access mechanism for multiple identical cores. well, I mean, that we had this chip coming that had these new, I mean, multiple identical cores, and we knew we had to somehow exploit they call it spatial redundancy. I mean, replication. And anyway, we came up with a pretty innovative way to do testing of multiple identical cores. And it relied on something that we did at Motorola also, was the first time we had an embedded core of any kind. I came up with I need a wrapper around this core, and I tried to get that patented at Motorola. No, we don't want to do that. Well, that was happily that was put into the public domain, that I was able to use it readily at my next employer with a defensive publication, and it's kind of it underpins 1500. But always looking at what gaps are there to do, and just really dig in and try to come up with something new, especially if you're on the bleeding edge. Another thing is, and this is hard to discuss. people even discussing this, I'm misunderstood sometimes. Avoid miscommunication. Oh, and this is just a human dynamic thing, and especially in engineering organizations. Oftentimes, especially in tests, you get moved around, between different teams. You get called in to consult on different projects and things like that. So different teams develop their own lexicon and methods and basic understandings and assumptions. And when you cross these boundaries of these different organizations, you're using the same English words, but they mean different things to different people. And people say something and they think they know that what they're communicating, and someone hears something and they think they know what they're hearing, but very, very often it's not the same thing. And so I say always check that you really get your terminology right. And I mean, oftentimes it's come up where someone's been talking for 2 hours and then they say something. Wait a minute. What? Say that again. Well, that didn't make any sense. You have to back up. When we were doing 1500, the standard, it took us about 7+ years. It was about the first 3 years of that. All we really accomplished was developing a common set of terminology, because everybody had their own terminology, and it was led to a lot of confusion. Like one of the things one of the terms we use in there, we talk about input terminals and output terminals. The reason we use that, and that's in the standard, is that was a term that wasn't already preloaded. Nobody claimed that to mean anything. So we found one that wasn't already taken instead of what's a pin anyway. So I just say avoid. You have to work really hard at avoiding miscommunication, and it really bogs things down when you fail at that. So that's a biggie. The other is think outside your DFT box, or test or whatever. But in DFT in particular, but other test fields, you have a vantage point. You have a view of other organizations often. In DFT, I say I have visibility from the production floor, the product engineers, the test engineers on the tester, and the tester architecture. I have some currency with that, some view of that, and over here, I'm with all the advanced design guys just trying to keep up with where they're going, right? And you see organizationally, even business things sometimes. Well, anyway, I say, especially in this area, look around and then see what contributions you can make to the bigger enterprise, besides just your keeping your nose down in trying to get your next chip out. An example is, and I wasn't there, but I've heard this from the horse's mouth. At Intel, in the early days, they're working on 386, and they're trying to come up with a better. They were doing fault simulation, and they for all that's their basis, functional patterns with fault simulation. And fault simulation is difficult. I think we know. And they brought in a consultant named Konstantin Temek, and he had some ideas about a BIST. And they kept him in a clean room. I mean, like no, they didn't show him any whiteboards or any schematics or anything, but they were picking his brains, and they got some ideas. And anyway, the guy who was doing the brain picking was Pat Gelsinger, and he did a BIST of the 386. Had a bunch of pseudo-random pattern generators and LFSRs, especially in the control stuff, and it was it helped their fault simulation a whole lot. Anyway, they used that in a lot of different ways. It was a big driver. They got lots and lots of mileage of that, and I think we can say Mr. Gelsinger got a lot of mileage out of that.
Good, thanks, Grady. Good lessons. So, Tim, you've seen all this from a different perspective, being within one company, and roughly the same kind of time frame. What are the lessons you take away?
I'd say the biggest lesson is my piece to publish more. Yeah, so I'd say that DFT, you really need to have good program management skills in addition to being good technically. And I'd learned that the hard way on one program where I kind of bit off a little bit more than I could chew. And as an engineer or project lead, you've always got to manage scope, schedule, and resources, and you've got sometimes need to make hard decisions about prioritizing what you want to do and making sure that you have those scope, schedule, and resources to do what you've signed up for, and make sure you communicate that effectively to the people that are counting on it downstream. So I was fortunate that I had supportive management when that happened, because you want to have supportive management that's you can tell the truth to, so that they have an opportunity to provide you help to make a course correction. If your management's always beating you up about missing schedules, then you're not going to be as willing to fess up to that, and it becomes too late once it's identified that it's a problem to make any course correction. And I've definitely been also in different projects where I've seen people get beat up for missing schedules, and then you get to play the game of schedule chicken. And it's kind of like the old story of you and a friend are taking a walk and you see a bear, and you just need to outrun. You don't need to outrun the bear, you just need to outrun your friend, right? So beware of schedule chicken. A lesson I learned early in my career was to not be afraid of change. I mean, change is inevitable, and it's not always a bad thing. Sometimes it can be an opportunity. I was still in a test engineering career path. I was a newly minted test engineering manager, and our director called us all into a meeting, he and all his managers, and he announced that there was going to be a reorganization. We're going to go from 3 groups under him to 2 groups, so there's going to be a merger. And as we're going around the room, one of the other managers commented, don't view change as a bad thing. Look at it as an opportunity. You may be on a path that you're just kind of blindly going along on, but there may be something else that you really want to do. And I thought about that and decided, I'm not really that into or passionate about management. I kind of do it out of necessity, but I am really passionate about doing DFT. So I took that opportunity to switch into doing DFT, and I've never looked back since. So that was a great piece of advice that I got. And kind of related to that is, I don't really have an anecdote to go with it, but Winston Churchill, I believe, once said that never let a good crisis go to waste. So look at those sorts of things as opportunities to maybe change what you're doing, to try something different that you've been thinking about. And also don't be afraid to grow your skills. I think we've heard in this conference about SDCs, and I think even the New York Times published something not in the recent history about SDCs as well. So that's certainly topical. And as you're growing your skills, don't only look forward and invent new things, but also look back at what's been done before. An example of something that maybe could apply to that SDC example is fault-tolerant architectures. There's just something that we can learn that's been done in the past that we can apply to today. What's old is new sometimes.
That's great. Thanks, guys. That, a dozen pieces of advice. It's like having a beer with you guys at 9 in the morning, but that's a lot of great career advice there. Thanks. All right, so let's round this out then and start talking about the future. So, we've got a room full of people who probably appreciate the description of how the industry evolved and how ITC helped with that, and the kind of lessons you guys took away over 128 years of experience. But what they're all worried about is, what am I going to do about the problem that comes up next? So let's talk about future challenges. So Mike, why don't you kick us off?
So I'm going to give you the most important piece of advice in this conference. If you're with Tim, the marathon runner, and the bear appears, don't try to outrun him, push him down first. Looking to the future, I think the same trends that we've seen in the past are going to continue. Our industry will keep trying to shrink the geometry, shrink how the transistors are built, get higher density. We're going to see continued levels of integration. You guys that haven't done SoC or die stacking yet, it's on your horizon somewhere down the road. So the biggest problem with that is that the number of transistors goes extremely high. And if you've looked at those papers, you know that the required coverage is a function of the number of transistors that are on the die. And so your fault coverage is going to have to get extremely high to deliver the quality that the industry demands. And like I said, when I was at Convex or back in the day, it was military, avionics, jet propulsion labs, or NASA. Those were the guys that said, we have to have this level of quality, and they took extreme measures to get there. But at this conference, you're learning, the server market, Google, they care about the small or the delays and defects, hidden defects. And it's like, okay, well, they're demanding that quality. If you're getting ready to go into automotive or already there, the automotive quality really has to be high. Or even today, I saw where some of our computers are being used to direct robots that are doing brain surgery. All right, so you can't have a glitch in the middle of that. They want the quality, as well as we want to make sure that you continue to have that quality, that it endures through time. Reliability. And we talked about thermal some. I think thermal is going to continue to be a problem. And since thermal heat is what generates destructive forces on the electronics, you're going to see more and more thermal DFT. You're going to see thermal telemetry. You're going to see, really having to understand that piece of the equation. I think that's what's in everybody's future.
Lots and lots of embedded instruments.
Okay. All right. Thanks, Mike. Tim, what do you see as the challenges coming up?
I guess we need to turn the AC off for that robot doing brain surgery. Yeah. So this is already happening in certain markets, right? But I think we'll see a bigger push for in-field testing. I mean, that's been happening to some degree in server already. It's certainly been pioneered and pushed more heavily by the automotive market. But the risk of degradation makes a strong case for more in-field testing and probably beyond those sort of markets. I think it'll just proliferate, and we'll see more and more of that in the future. And related to that is something Mike touched on already, and Grady as well, that we'll start to see a lot more use of embedded instruments. So you need to be thinking about what sort of things do we need to put in our devices that we could use to monitor health of devices in the field, or if something happens, how can we do data collection with the instruments that we have to make some change or be able to know or understand what's going on, so we're not in the dark. And it really all comes down to how test adds value. So think features, not overhead. DFT done right is a game changer. Lack of DFT is uncontrolled risk and expense. So I guess an example to maybe further gel something that Mike touched on is if you have a device that has 100 billion faults and you get 99.99% fault coverage, you're patting yourself on the back and thinking you're doing pretty good. But think about how many faults that leaves untested. 10 million faults. The scale of devices that we're dealing with, that's a huge problem. And how do we deal with that? Is that going to be RAS? Is that going to be maybe some lessons from fault-tolerant computing? Is that going to be use of these embedded instruments? Some combination of all those, or something yet to be invented? So think about that. So.
Great, thanks, Tim. Grady, why don't you go ahead and bring us home? What do you see as the challenges in the future here?
Well, I worry about the profession somewhat. I mean, where are we going to get our DFT people? And I think it's on us to bring each other up and encourage the younger generation, or there are people that are considering this, partner with academia, different ways to pass on knowledge. I mean, I like to participate in the ITC and write papers myself, so I can help with that trend. But one of the big things is cooperation and collaboration between industry and academia. So like forging new relationships with like, if you have a professor that you know, or you think you could know, have some interactions with them and collaborations with them. Like you could be an SRC liaison. I mean, for a project with the SRC, for instance, that's an example. You can, hire interns. There's lots of things like that with collaboration between academia and industry that would be helpful. Anyway, I try to be a mentor to the young people coming up. One of my last little words, I just can't go without, I can't turn out the lights on this career without putting in a plug for LSSD. And in the future, I think it still has a role. There's most things, you can do most things. You can do a really good job most things with MUX-D, but there are some things you cannot do with MUX-D. I mean, and LSSD, I mean, the flops are 60% bigger on average. but they don't have a performance penalty. So that may be your problem is you can't, you're chafing, or your designers are chafing with the performance penalty of the MUX for MUX-D. You're trying to be competitive to get higher speed or something. That might be a place where LSSD can come in. Or, I mean, there's all these different architectural things. There's something called L2 star. I'm trying to channel Tom Williams here. I've done things with source synchronous buses and dual edge flops. You can't do those with MUX-D. It just doesn't work. But LSSD is very amenable to that. So I mean, anyway, if you find most of the time MUX-D does it, but if you find yourself up against the wall on some bleeding edge thing, pull out MUX-D and look at it. That's my last thing to say.
LSSD.
I mean, LSSD, and look at it, yeah.
All right. Thanks, guys. I really appreciate you sharing all the wisdom there. But one thing I noticed wasn't on any of your bullet items here is I'm sure this audience really wants to know, what are we going to do about testing quantum computers?
I don't know, man.
We got a flight to catch.
Golly, let's let me out of here.
So this is what happens when you ask the experts. All right. Come on back, guys. Hey. So again, seriously, thanks for sharing all that wisdom. That's a lot of great experience. So we've got a couple of minutes. The next session starts at 10:30. It's 10:12 now. So we got a little bit of time for Q&A before you guys drift away. So anyone have any questions? Go ahead. Hi, Jeff. Hi, Shankar. Tell us, everyone, who you are.
Can you hear me okay?
Yep.
Hi, my name is Shankaran Menon. I'm with Intel. Hi, Grady and Tim and Mike. I've known you all for many years from Austin. So it's good to see. Jeff, this is a great format. I really like it. I'm sure we all like it. So the question I had two-part question, right? So we had first the gigahertz race, right? We had more and more transistors going in, Moore's law still alive. And then we had the arms race.
There's a big echo. Can you just slow down just an eensy bit?
It's a bit slowed down. Okay, I tend to speak too fast. I'm going to slow down now. Is this better?
Yes.
Okay, good. So then we had the arms race, and now it's cores race, right? As the device shrinks, we have more and more cores, 32, 64, 128, 256 cores. Now, design will put in as much as you can, but then they throw it to the DFT people and say, hey, you go figure out how to test it, right? So now the test challenge is that test data volume, test time, eventually it comes to test cost. So now the test cost is approaching the cost of the part, right? And thanks to our can you still hear me?
Yeah, it's better, actually.
Okay. So thanks to our EDA friends, Janusz and Synopsys and Cadence coming up with streaming scan network, fabric scan, other methods to reduce the test data volume, reduce the test time. Now, as we move forward, it's going to get worse, right? If the test time and the test cost, right, finally the cost, becomes same as the part cost, then it becomes economically non-viable. What is the evolutionary way or revolutionary way by which we can improve the test cost is question number one. The second is when silicon comes back, you know the scan patterns are failing and you have time to debug, right? You need to debug. That brings the time to market. So debug, and then you have functional debug. We have standards. You talked about JTAG standards. Now, we also have standard that we are working on for scan and array debug called P2929, which you are aware of. Now, how do you think all this is going to play with to help improve debug? And then you have closed chassis debug. The moment you take the chip, it's a pre-RQ'd chip, you put it in a box, Dell loads operating system, and then you see blue screen of death. Now, you can't open up the part. You want to do closed chassis debug and not open chassis debug. And then you have in-field debug. You have SLM. How does all this play with in terms of debug is my second question. So it's a two-part question.
You guys want to handle the test cost question first? We've heard that before in this, this kind of forum. Pat Gelsinger in 1999 talked about test costs exceeding device cost, and now cost of test of these gigantic, multi-die chiplets.
Sure. So test cost is largely amount of how much test content and the bandwidth you have to apply it, and and the cost of the AT itself. And I think as we move into automotive and everyone's talking about we need in-field test, right? In situ test. You're going to develop those methodologies where you can test from a simple structure, and SLT is a simple structure. You're going to start applying those patterns there. Use a less expensive test platform with a higher bandwidth to control the test cost. In terms of how do you debug something like that, I think you have to set management's expectations. When I talked about our supercomputers, it was multiple bays, multiple card cages, multiple boards in every card cage, and that's what a chip is today. So if you think the time you spent debugging your old simple part is going to equal the time it does to do a whole multi-core supercomputer on a chip, that's just setting expectations, and the industry will have to pay for it, or else the product isn't worth doing. So you can't go down the same roadmap and think there's no penalty to pay. That has to be an economic decision made by whoever's doing your product roadmap.
And I think I touched on a little bit in my early part of my talk, where the number of pins that we've had access to has been fairly constant, but what we're trying to test has grown exponentially. Yet we seem to keep being able to invent new ways to kind of keep pace with that. And I don't know exactly how that will evolve over time, but it seems like we've been able to manage that, come up with creative ways, whether it's ourselves doing some invention or EDA vendors doing some invention. So I think that challenge has always been there and will continue to be there, and we'll continue to find ways to work around it. So.
Bandwidth and different, hierarchical, levels of compression stuff. I've never been the best debug guy, I have to say, but definitely you have to find ways to have access to these things. Embedded instruments where you can take different kinds of snapshots of, gain information about, like Mike talks about all the voltage gradients and temperature gradients. I love that word gradient anyway. I just love that. But anyway, so the embedded instruments to be able to understand what happened. What the local environment, micro environment, what is when failures happen, and different ways to get timestamps and signatures and things like that. But those are the embedded instruments to help with that debug. But also, we've got to have lots of, more and more bandwidth, or we'll fall behind. We won't be able to get the ball across the goal.
Did you say gradient, and you're going to continue your work and not retire?
Who, me? Continue?
Yeah. Did you just say gradient? Gradient?
Oh yeah.
Thanks. Dave, come on up. We got time.
Didn't know if you had time. Really nice trip down memory lane. I couldn't believe we actually ended on LSSD. Interesting.
Get closer to the mic, Dave.
I couldn't believe that we actually ended on LSSD.
I'm just a dinosaur. I just feel like I just feel like I have to say that before I go out, because I see people not being mindful of that
Absolutely.
opportunity.
And Tom would appreciate it as well, and it was really good for a while. Key to what you're talking about is structural test techniques. DFT was probably the most common word you all used. And obviously, I have a gray hair to know that we didn't start that way. Functional test was the norm, at least when I started.
Yeah.
Functional test is still here today.
Yeah.
Look at
we still
mission
have to do all
mode
that.
and native testing and all those things going on there. After looking from your experience base, what's the balance? What is the role of functional test moving forward?
So when we're talking about quality and we got to hit to really, really high coverage, that's not just stuck at. That's all of the AC faults that exist in the design too. And your ATE's only got a certain amount of memory, only a certain amount of test content. So if you're using that for your structural test that's DC coverage or a few AC faults, you're still using the SLT functionally to try and hit a lot more speed pass through the design. The nice thing about SLT is it doesn't have an artificial environment. Like I say, well, you put a thermal head and you force the memories to be hot when they're not really hot, that part's not running the way that it runs natively. And testers are synchronous, and these devices all have asynchronous interfaces all over them now. So I think the SLT is attacking that functional speed path area you're talking about, why we still need it.
And functional test, I think, stresses the part in different ways than structural test does. The whole environment is different running a functional test than a structural test. The difficulty with the functional test is how do you get a good assessment of what kind of value it's adding, right? It's hard to quantify it.
You know, one other point about that around structural test is back in the day, everyone worried about thermal viruses. We would actually write patterns to try and create a thermal virus that would do a hotspot. So if you went and ran a speed test when the part is cold versus when it's been looping on a thermal virus, you got totally different results. And that's right back to it stresses it a lot different when you're in a native mode executing code versus just a structural test.
All right, thanks, guys. Heiko, last question.
Heiko Ehrenberg, Group Electronics. I don't really have a question, I have a comment. I may be one of the few board test engineers here, and I really appreciate all the work you do. So keep it up, but I think the one piece that might be missing sometimes is communication. We don't necessarily know of all the fancy stuff that's inside your chips, and a lot of it might actually be useful at the board system level for monitoring, collecting information.
Could you get just an inch bit closer to the microphone, please?
So communication between board and chip test industry, I think, is very important to get the board test engineers to understand what's available, what they can use at the board and system level tests, so that we can benefit of all the stuff you do.
Very good point. And for those of you who don't know, Heiko is the chairman of the 1149.1 refresh effort. So he's got a vested interest in
anybody
doing
who wants to join.
Yeah, please join in and help. But yeah, I think this whole point about the ecosystem that exists between chip test, board test, system test, test, debug, everything. There's a lot we can do as a community to tie this together. So
And chips can help board tests with some of the embedded instruments. The board test guys could probably use some of the some of the benefits of the embedded instruments.
Yeah, back in the day for our convex as part of the board test, one of the things we did is put 2 registers at every IO for X test. And you could put it in a mode so that you could toggle any pin, or you could set up the pattern you want to toggle, everything going 1, everything going 0. And that gave you a good ground bounce test, or you could go do AAs or 5.5s and look at interference between the signals and all. And the thing I would say is 1687 is all about developing tests in a way that can be transported, retargeted in different environments. I think maybe board test needs to look at what needs to be in 1687 to augment it to help you.
all right, and we don't have any questions online, so I'm going to call it here. We got 5 minutes before the sessions. Thanks again, everybody, and let's thank our speakers.